Alrighty, in this video we're going to go ahead and put together some of our methods as well as our horizontal movement. So let's go ahead and make sure we have Visual Studio open and that we're looking at our character controller 2D file. So we're going to be putting together again some of these methods that relate to horizontal movement. So first of all, something that I want to do is our velocity right now is a public property, but some of these methods I kind of want to be able to modify the individual components of our velocity without having to reassign our velocity entirely. Well, let me show you guys what I mean. If we go into add force, for example, we can simply say velocity plus equals force. If we go into set force, we can say velocity equals force. However, if we go to set horizontal force, watch what happens when we say velocity.x equals x. We get an error. We get an error that says cannot modify the expression because it is not a variable. You might be looking at this code and being like, well, it's x, it looks like a variable to me, but the compiler does not see it that way. The reason is vector2 is a value type. It is a structure. Value types are passed by value. Every time you pass a value type to a method or return a value type from a method, you get a copy of that value type. As a result, when we access velocity through a property, what we're getting back is a copy of velocity. So when we say velocity.x, we're actually modifying the x component of the copy of velocity that was returned by the property, and not the actual data itself. And because this is such a common error, Visual Studio, or rather C#, prevents us from doing this in the form of an error, because it's so common that a person might make this mistake somewhere. They've actually made it impossible to do this. And that is just telling us that what we're doing is we're doing something that is actually different than what we think we're doing. So what I want to do is I want to make it so velocity is a property and publicly accessible, but I really want to lock down accessing velocity to these methods: add force, set horizontal force, and set vertical force, just because I just kind of like that convention. I think it's a little bit cleaner as far as handling this sort of thing, and it makes it so the implementation detail of character controller 2D is hidden, because maybe we might in some cases want to change how the forces that we're adding to our character controller relate to its velocity, and by hiding them behind methods, we are able to do that. However, to fix this problem, we simply have to convert this public vector2 velocity from a automatic property to a property with a backing field. How do we do that? Well, let's start off with creating a field. So I can say private vector2 underscore velocity. Then, instead of having this as an automatic property, I'm going to change this to be a normal property with just a getter that just returns velocity. So this vector2 velocity method now returns a copy of velocity. However, we now have this private field that we can access and manipulate in the ways that we want to. Again, we can't do velocity.x equals x because the property velocity is actually a method, and methods that return a value type return copies. Therefore, uppercase velocity, since it's a property, returns a copy of our velocity field. So now that we've added the velocity field and we've changed our property to simply return that velocity field, we can modify our add force, set force methods to modify the field and not the property. So now I can say velocity.x equals x. Notice how I'm saying underscore velocity. That references the field, which I can manipulate its components of. I cannot manipulate the components of a vector that is returned by a property. So then let's go ahead and do that on set vertical force. Set vertical force will set velocity y equals y. Okay, so that is our awake, add force, or part of our awake: add force, set horizontal force, and set vertical force. So those are our public APIs for manipulating how we want the player to move. However, we still have a couple things to do. Inside of our awake method, we need to add some initializations for our controller, in addition to the initialization we already have for our state. So basically what I want to accomplish is aliasing out some of our components into private fields. Now, we don't actually have all those private fields yet, so we'll go ahead and write them. In addition, we also need to pre-compute some values. Remember this diagram from before? So let's say in this diagram, it's showing that we have 3 vertical rays that are being casted, right? And in this case, we have 1, 2, 3, 4, 5, 6, 7 horizontal rays. We need to calculate the distance between each one of these horizontal rays and each one of these vertical rays so that they are evenly spaced out between our box collider. So what we're going to do in our awake method is twofold. A, we're going to alias out commonly used components such as our box collider and our transform into individual components or individual fields. We're also going to do the same thing for our local scale. Then we're going to calculate the vertical and horizontal distance between all of the rays by taking the size of our box collider and dividing, let's just go with dividing it up into a number that determines the distance between each one of those individual rays. Did that make sense, or did my terrible abuse of the English language confuse everyone?
I like human language that you were going to say.
I stopped myself. I can't believe that's... Oh, that means it made it on the recording. I'm terrible. All right, so let's go ahead and get started.
It means you think in a very worldly manner. That's a good thing.
It kind of means I think in the opposite. That's like implying that our language aren't human. Okay, so let's go ahead and add in our private fields. And obviously, no, I don't believe that other languages aren't human. The private fields that we're going to want to add are going to be the things that we want to alias out. So we want to alias out our transform. We want to alias out our vector3 local scale. We'll be using our local scale in a lot of different places in this script. We want to factor out our box collider 2D. So we'll call this box collider. So those are the things that we want to kind of have always around for us. Then we need to make sure that we write some sort of float values that determine the vertical and horizontal distance between rays. So for example, private float vertical distance between rays. What does this variable contain? It contains the vertical distance between rays. Then we have the horizontal distance between rays. Okay, so now what we have to do is we have to fill in each one of these variables. Let's start with the easy ones. The easy ones are just the aliases that we have, our transform, our local scale, and our box collider. So transform equals transform, local scale equals transform.local scale, and box collider equals get component box collider 2D. Of course, the character controller 2D will assume that we have a box collider 2D on the same game object. I want to point out that aliasing out things like transform and local scale will only make things marginally faster. However, sometimes I do it, sometimes I don't. And in general, the property called transform, so if we decompile this by hitting F12, we'll see that this is a property that returns this.internal get transform, which is a call that calls into the C++ implementation of Unity. So it does have a performance impact when we access it all the time. By aliasing it, we're removing that performance impact. However, it is very slight, and I typically don't do it. But in cases where I know things will be very transform heavy, I just kind of like to do it. Okay, so next up, let's go ahead and compute our vertical distance between rays and our horizontal distance between rays. That's actually very straightforward to do. All we have to do is we have to take the size of the box collider and divide it in equal parts, or not equal parts, but we need to get this distance right here. So what we're going to do for example, for our horizontal distance, or let's do our vertical distance. So what we're going to do is we're going to take the size x of our box collider, multiply it by our transform scale, then subtract 2 times the skin width. So we'll be moving kind of into the box collider. Actually, let's go ahead and I'm gonna bring my tablet up here on my desk so that I can actually show you guys this algorithm and why it works. So what we're doing is we are working with the wrong color. What we're doing is we have a box. So this is our box collider, right? This is our box collider 2D. And what we want to do is we want to get a distance between rays. So let's say we have 3 rays right here. We want this distance as a number. So what do? Well, we take the size of the box collider. So the size of the box collider might be this far right here. Then we add it to the scale of the object. Remember, if an object scales up, so let's say that the box collider was originally only this big, but we scaled it up to be bigger because we scaled up the player. Well, that means that what we would have to do is multiply this by our scale of the player so that we get this full length. Now we have a number that represents the full length from one extent of our box collider to the other extent of our box collider. Remember, this first green line is the box collider's width. The second green line represents the scaling that we might have done on the object. So now that we have that number, which will represent as this line, we can't divide it just yet. The reason we can't divide it up just yet is because we need to account for our skin. Remember, our rays are going to be casted through a skin. So I'm going to use a reddish color to show the skin. So the skin from the left-hand side might be this big, and the skin from the right-hand side might be this big. So the number that we really want out of this calculation is going to be this number, this distance between the between the box collider. So again, box collider size, player scaling, then we have the skin. How do we get rid of these 2 red bits? Well, we take the width of a skin, we multiply it by 2, and then we subtract it off this. So we'll get a total width of like this. So this will be our final width. Then we cut it up into 2 parts. The reason why we cut it up into 2 parts instead of 3 is because if we cut it up into 2 parts, we'll get a division there and we'll get a division there. And then that will give us the width or the distance between each one of the components. See what happens if you take this number, divide it by 2, we now have a number, this number right here, which gives us the length that we need in order to represent the distance between one of these rays and the next ray. Does that make sense? I think I killed Steve.
It does indeed, sir.
Oh, maybe I didn't.
No, I said it does indeed.
All right, sweet. I just wanted to represent that graphically because I want to make as much of this not look like magic as possible. So there is a geometric interpretation of most of what we're going to do. Okay, so how do we turn that into code? So we've defined what we want. How do we turn that into code? Well, the first thing we do, let's calculate our horizontal distance between rays because that's the example that we used. The vertical distance between rays will be the exact same algorithm. So what we're going to do is we're going to say collider width equals box collider dot size x. Then we have to scale it up by our transform local scale x. Then we have to subtract off 2 times skin width. Remember, the skin width, that's the red bit. That's the red bit right here. That's why we're subtracting 2 off of it. Once we do that, you'll also notice that I say mathf.absolute transform local scale x. The reason I do that is if you recall, when we flip our player, we invert the local scale. So we've already determined that inverting the local scale to like -1 is a valid thing to do with one of our players. Therefore, we have to account for that inside of our character controller. So what we do is we get the absolute value of the local scale x, and that's what we scale up our size by. And then we subtract off the skin. Now the last thing we have to do is we have to add, in this case, let's say there's 3 vertical lines. If there's 3 vertical lines, then we cut it into, we add 2 slices, and then the number we get left over is the distance between each one of the slices. So how do we calculate that? Well, we just simply say horizontal distance between rays equals collider width divided by total vertical rays minus 1. And that's where that minus 1 comes in. Because we have 3 total vertical rays in this example, we need to make 2 slices, 2 cuts into that line in order to get that number. All right, let's go ahead and do the other dimension. Let's say collider height equals box collider size y times mathf abs transform local scale y minus 2 times skin width. Vertical distance between not velocity. Vertical distance between rays equals collider height divided by total horizontal rays minus 1. So the vertical distance between rays is the exact same algorithm, except we're doing it this way instead of this way. Okay, so now we have our horizontal distance between rays, our vertical distance between rays, we have our state, transform, local scale, and box collider, and we have our add force methods. So now what we want to do is we want to go ahead and start our actual implementation of our late update method and our move method. So our late update method currently is not going to be complete, nor is our move method. But we will write just enough code to make it so we can move horizontally. And then we can test that. So we want to implement this piecemeal. So I broke up the controller into different features, moving horizontally, moving vertically, handling slopes, and then finally moving platforms. With gravity and jumping in there somewhere. So remember, the late update method is invoked after all the update methods of all the other objects are invoked. So we know that if any of those other objects need to do certain computations, those computations have been done. So we definitely want to do this in a late update. What we're going to do is, this is going to be pretty simple. We're just going to type in move velocity times time dot delta time. That's it. Yeah. It looks like it's really trivial that we even added a move method. Like, why do we even add a move method when we have a late update method? But in reality, the move method could be useful in more cases than this. In addition, the move method, I might decide to make it public. Currently, I'm making it private because there's no immediate reason why it should be public, and I like private by default. But the move method, conceptually, I really want to be its own entity. Okay, so let's go ahead and write the move method. Actually, you know what? I can write pretty much the entirety of the move method by just depending on these method stubs that I've written before. So let's go ahead and do that. I'm going to say var was grounded equals state is colliding below state.reset. So what do we do when we move? Well, we keep track of if we were grounded. Then we reset the state. And if you recall, resetting the state, if we move over here, resetting the state simply sets all of these booleans to false and sets our slope angle to 0. So that's what we want. After we do that, we'll go ahead and we'll say if handle collisions, which we haven't implemented that boolean yet, but I am gonna, because there are so many variables that we need to add to our character controller 2D, I'm just gonna be adding in those variables, like those different properties and stuff, as we go along. So I'm gonna say if handle collisions. I know this code won't compile because we don't have a handle collisions yet, but I'm gonna go ahead and write the entire move method and then add the things that we needed back in. So say if handle collisions, meaning we are handling collisions, if we're dead, we don't want to handle collisions, then handle platforms is the first thing we want to do. Platforms will handle moving platforms, which would actually be a better name for this method. Then we want to calculate the ray origins. Again, what that method does is it calculates where our rays are going to originate from in an absolute sense. So we know how many rays we have vertically and horizontally. We know the distance between those rays vertically and horizontally, but we don't know where those rays start from yet. And that changes on every frame because where those rays start is determined by the player's position. The player's position can potentially change per frame, meaning every time we move, which is every frame, we need to make sure that we recalculate the ray origins. And these ray origins are shared between all the different methods that we might use in the class. Then I'm going to say if delta movement.y is smaller than 0, if they're moving down, for example, if they're being affected by gravity, and they were previously grounded or they're currently grounded, that means we need to handle the vertical slope. So this means if they're going down, either being affected by gravity or whatever, most likely being affected by gravity, and they're on the ground, that means they're potentially on a vertical slope, and we want to handle that possibility. So what I'm going to do is I'm going to invoke handle vertical slope, and I'm going to pass in ref delta movement. Again, I pass in a reference to delta movement as opposed to delta movement itself, A, because the signature only accepts a reference of vector 2, and B, the reason we need it to only accept a reference of vector 2 is because vector 2 is a value type, and handle vertical slope may modify my delta movement for whatever reasons. Next up, I want to say if math abs delta movement x is greater than 0.001f, then move horizontally, ref delta movement. So if they're moving to the left or to the right, which the absolute value of delta movement x is greater than 0.001, then move horizontally. So we're not going to be doing things like casting rays for horizontal movement if they're not moving horizontally. We'll decide if they're not moving horizontally, then there's no reason to do any checking in that case. Finally, we're going to be invoking move vertically, ref of delta movement. Of course, we do move vertically always because we will always have some sort of vertical force being applied to our character, typically via gravity. Next up, we're going to finally do our movement. We're going to do underscore transform dot translate, and we're going to pass in delta movement in the world space. So we are moving the character by delta movement in the world space. By now, if we are handling collisions, platforms have been handled, vertical slope has been handled, horizontal slope has been handled, and vertical movement has been handled. So all of this stuff has been handled, and we passed in a reference to our delta movement. If we get this far and we are handling collisions, that means our move horizontally method and our move vertically method have already modified the delta movement so that it doesn't result in an invalid move. They've already casted the rays to ensure that a player isn't trying to move into a wall or move below the ground or whatever by most likely setting the y value of delta movement to 0. Or in the case where the character is trying to move into a wall, it might change the delta movement's x value to 0. So by this time, in this method, transform.translate will represent the delta of movement that we want to perform in this step. Then what we want to do is, this is where things get a little crazy. I'm debating whether or not to add this code in now or wait until we handle the platforms. I think we're going to come back to the move method when we start to handle our stuff. Yep. Ignore me. Anyway, next up I'm going to say if time.delta time is greater than 0, then our velocity equals delta movement divided by time.delta time. So however much we changed or successfully changed, we want to go ahead and consider that to be our new velocity. Finally, we want to do a couple more things. We want to say velocity.x equals mathf.min velocity.x and parameters which hasn't been implemented yet, do not do default parameters here. Type in parameters, and parameters has not been implemented yet, so keep that in mind. Max velocity dot x, and then velocity dot y equals mathf dot min velocity y parameters, again, not default parameters, max velocity dot y. So we're clamping our velocity to the maximum and x and y velocity that was defined in our parameters. The final thing I want to do is if state dot is moving up slope, then our velocity y is 0. Or sorry, our underscore velocity y is 0. And we'll talk about that later. Again, I will go ahead and I'm just going to put a comment right here. I'm going to say to do handle or additional moving platform code. So we're going to add some code right there in a later video when we handle moving platforms. Okay, so that's our move method. Before we move on to the last method that we're going to be implementing in this video, which is the move horizontally method, I want to go ahead and add in our parameters property and our handle collisions property, because these are two properties that we're going to need for our code. So what I'm going to do is, actually, I'm going to say split. That's the wrong kind of split, Visual Studio. Way to go. I'm going to go ahead and say swit or window, and then I'm going to say new window, and then I'm going to open one on the right and one on the left. So people who want to look at the move method that we just implemented can do so, while I come up here to the top of this file and I add my two properties. So my handle collisions method, or property, I'm going to add that right underneath my public bool can jump property. The reason I'm doing that is because I like to keep my properties nice and grouped together. So I'm going to say public boolean handle collisions get set. Now it's important that handle collisions has a public getter and a public setter. That's so that other components in the system can go ahead and tell my character controller whether or not it needs to handle collisions. Okay, so now we have to do parameters. So what is parameters? Well, parameters, as you can see, is what we're using to pull information such as our max velocity out of what we had set up already with our default parameters. We have default parameters, but I want these to be overridable. I want it to be possible for some condition to override our parameters entirely. Because of that, I'm going to do two things. A, I'm going to add a private controller parameters 2D field to my class, and B, I'm going to add a public parameters property. The public parameters property will choose one of two things. Either A, the new controller parameters 2D field that we're adding, or B, the default parameters if that field is null. So what does that look like? Well, I'm going to go ahead and say private controller parameters 2D, and I'm going to say override parameters. Then, as a property, which I'm going to add up here next to my other properties, I'm going to say public controller parameters 2D parameters with only a getter. It only has a getter, it won't have a setter. It's going to be return override parameters null coalescing on default. All right, so what's going on here? Well, this parameters property will return our override parameters. However, if override parameters is null, it'll return default parameters. This is using the null coalescing operator. The null coalescing operator is equivalent to me saying if override parameters is not null, return override parameters, else return default parameters. So basically this public property, if I access my parameters through this property, it'll return one of two parameters, either the override ones or the default ones if the override ones don't exist. That means we can now override our physical parameters of our character controller 2D by setting this override parameters field to whatever we want. Sound good?
It sounds good, buddy.
Sweet. All right, I'll go ahead and close out this this other tab here, and let's get moving. Before I do that, I do want to point out late update. I don't think I talked about this too much. Basically, all late update is going to do is it's going to move the character per his velocity, scaled by time. So if he's moving 5 units to the right, that means he's moving at a velocity of 5x, and then we want to multiply it by time, delta time, which delta time is a number that represents how many seconds have passed since the last frame. Very commonly, delta time will be a very, very small number, under 1. The only time delta time will become over 1 is if you are only have like, what, 1 frame per second or something like that. Yeah, you'd have to have 1 frame per second to have a time delta time of over 1. So anyway, so we move the character along his velocity, and that's cool. So that is our move method. That is our late update method. Let's go ahead and handle our calculate ray origins method. That's because we need to implement our calculate ray origins in order to implement our move horizontally method. Okay, so how do we do this? Well, we need to calculate 3 potential raycast origins. So let's look at what that means. So let's come back into Photoshop, and I'm just going to delete all this stuff out. Blah, blah, blah. Actually, I'm just going to delete the whole thing. Then I'm going to select white, draw a box that represents our character. Okay, there are 3 raycast origins that we need. 1, we need raycast top right. 2, we need bottom left. And 3, we need bottom right. So, why do we need these? Well, let's say that we are moving to the right. Let's say we are moving to the right and down. So let's say our velocity is 2 units to the right and -2 units up. And of course, -2 units up is 2 units down. So this is what our velocity vector looks like right now for this example. That means I have to raycast on the right and I have to raycast on the bottom. So how do I perform that? Well, in this case, I will start in my horizontal movement, I'll start placing my raycasts right here at the bottom right. So I'll go ahead and place one here exactly at the bottom right. Then I'll move up. Remember that number that we calculated before? The what did I call it? The vertical distance between rays. This is that vertical distance between rays right here. And then we go up here and we raycast again, and then we raycast again, and then we raycast again, and then we finally raycast at the top. So it might be a little bit better if I use a different color for that. So this is, that reddish color is the vertical distance between rays. This point right here, the bottom right, is the ray origin. So we need to calculate that ray origin. We also, because we're moving down and to the right, we also need to raycast here. So let's say we were raycasting here. Well, we'll start here at the lower right, or lower left, sorry, and then we'll do a ray, and we'll use the horizontal distance between rays, and that's going to be our stepping factor. So we'll raycast once here at the origin of our bottom left, we'll step forward distance between rays horizontally, do another raycast, then we'll do distance between horizontal rays, and so on, doing a raycast at every point in order to get our X amount of rays being rendered. But again, for all this to work, I need to know these three origins. Because for example, let's say instead of moving down and to the right, let's say I was moving down and to the left. If I'm moving down and to the left, that means I will need to know, or I'll need to cast out these rays and cast out these rays. And in this case, I can use the top left and I can use the bottom left to calculate the origin for these two. So I start at the top left or the bottom left and I move horizontally or vertically. I can do this for all the different combinations because we can move down into the left, we can move up into the left, we can move up into the right, and we can also move up, right. Wow, that is not an arrow. Up, right, down, left. So we need to handle all of these cases, and we can handle all these cases by calculating the ray origin for these 3 points. That point right there, that point right there, and that point right there. So how do we calculate those? Well, what we need to do is we first of all need to determine the size of the box collider. So what's the size of the box collider? The size of the box collider is going to be the size of the box collider plus the scaling of the player. So we'll get this number right here. That's represented by these 2 lines. So we have to get the size of the box collider, then we have to scale it up by the local scale of the player. Then we need to know the center of the box collider. So the center of the box collider is probably going to be right here. Probably, but it might change. Right? Then what we need to do is we need to figure out, let's say the raycast top left. What's the raycast top left going to be? Well, it's going to be the position of the player, which let's say position of the player is P, and P is right here. It's going to be the position of the player plus the center X minus the size X plus the skin width. So it's going to be the center, which is also here. So it's going to be basically P plus, and then the center minus size minus skin will give us the top left. So the position of the player, the center, added to the center, which will basically give us a number, or it'll give us a vector that's somewhere around here. And then we want to subtract off the size of the X, which will give us a number that's right about here. And then once we do that, we have to subtract off the skin width, which will bring us in. Remember, the skin width is going to be negative. So again, we start at the position, we move up here to the top right, we move to the left by subtracting the size, and then we are pretty much done. Sound good?
Sounds awesome. Just don't make a mistake or you'll turn everything else in the universe at a right angle to yourself.
That could potentially happen, I suppose. Anyway, all the other algorithm or formulas for determining the other start positions, the bottom left and the bottom right, are just variations of that. So for example, the raycast bottom right, figuring out this origin. Remember, I'm working in world space coordinates right now, so I'll specify that by placing an origin right here. That's a really, really bad origin. There we go. So we're working world space coordinates right here. So to get the bottom right, we take the position of the player, we add the center X, and we add the size X, and we might subtract the... so we add the center X, and we add the size X. I think I might be getting this backwards, but either way, the math will work, and then we subtract the skin width. That's actually going to go the other way around. And then we get the skin width. Again, that might be backwards, but anyway, the point is that this method will give us 3 vectors, and those 3 vectors will make casting our rays a lot easier. Which actually reminds me of something. We don't currently have anywhere to store these 3 vectors. So let's go ahead and I'm going to write this method, and then we'll be depending on 3 fields that haven't been written yet. Okay, first of all, we need the size of the box collider. The size of the box collider is going to be a vector 2 of box collider size X scaled up by local scale X, and then box collider size Y scaled up by scaled up by math abs local scale Y divided by 2. Okay. So again, that is going to be a vector scalar division resulting in a vector that is scaled down by 2, in half, I mean. Next up, we need our center. So our center is going to be new vector 2. We're going to pass in box collider center x times local scale x, box collider center y times local scale y. So that'll give us the center of our box collider. Now we can do our raycast top left, which is going to be equal transform dot position. So that's our position. Then we're going to add center x minus size x plus skin width, followed by center y plus size y minus skin width. So again, we're starting at where we are currently located, and then we're adding on the center of the box collider, which is relative to the actual center of the, this is not going to be in world coordinates. Subtracting off the size x, so this will bring us to the left, and then we're adding skin width. Then we do center y plus size y. Center y plus size y plus position will result in the top, because we're going up. And then we're subtracting skin width. That's why it's the top left. Raycast bottom right will equal transform position plus new vector 3, center x plus size x minus skin width. So we do center x plus size x. And if we do center x plus size x, if we notice in Visual Studio, that will give us a position here. That's our player's position. And then we add the center value, and then we're going to add the size value as well. So we get the center, and then we get the size. Remember, the center is probably going to be, stuff and things. The most important point of what I'm trying to make here is follow the operation that we're doing. Are we adding or are we subtracting? And that'll kind of tell you the direction of where we're going, even if the actual formula might be a little confusing. So if we do center y minus size y, that means we're going down, and then we're adding skin width. So we need raycast bottom left is transform dot position plus new vector 3, center x minus size x. What is center x minus size x? That's to the left. Plus skin width. If we're going to the left, we need to add skin width. Why? It's because the skin goes deeper. And because it goes deeper, if we're going to the left, we want to now go a little bit to the right per our skin width. Then we do center y minus size y. What is center y minus size y? That's down. And because we're going down, we need to add our skin width, because we go down and then we add our skin width, which results in us going up. Okay, so that's our raycast top left, bottom right, and bottom left. These are all going to be vector 3s. So let's go ahead and scroll up all the way to the top, and let's add these private fields. So I'm going to go ahead and say private vector 3. I'm going to say raycast top left. Oops. Raycast bottom right. Raycast bottom left. And as you see, all of our errors went away. That's because now that we've assigned defined, or rather declared, raycast top left, bottom right, and bottom left, this code down here will now work. Okay, now let's go ahead and finish our last method, our move horizontally method. So what's our move horizontally method going to do? Well, it's going to cast a bunch of rays to the right or to the left, depending on if we're moving right or left. And then it's going to constrain our movement based on that raycast, or the result of that raycast. So let's go ahead and do that. First of all, is going right. How do we determine if we're going right? Well, we check if the delta movement x is greater than 0. Next up, ray distance, which is going to be mathf abs delta movement x plus skin width. So what is ray distance? Well, let's go ahead and actually, I'm just going to type the stuff out and then I'm going to diagram it out after we're done, so we're not constantly switching back and forth between Photoshop. So we have the ray distance. Next up, we need ray direction. What's the ray direction? Well, the ray direction is going to depend on if we're going right or left. So we're going to write this as a ternary. We're going to say ray direction equals is going right, question mark, vector 2 right, or negative vector 2 right. Why do we do negative vector 2 right instead of vector 2 left? Well, that's because vector 2 doesn't have a left property. For whatever reason, vector 3 has a left constant, but vector 2 has no left constant, meaning we can just negate vector 2.right and result in having a vector that points to the left. If you're curious about what the definition of right is, all the definition of vector 2.right is a vector that's going in the right direction as opposed to the left direction. Also, it has a unit length. All right, so that's our ray direction. Next up, we need our ray origin. What's our ray origin? Well, we just talked a whole lot about ray origins. It's going to depend on if we're going right or left. So if we're going right, we want raycast bottom right. If we're going left, we want raycast bottom left. Sound good? Okay, so let's go ahead and say
Yes, indeed.
Sweet. So let's go ahead and loop through all of our rays that we want to cast. How many rays do we want to cast? Well, we'll loop for var I equals 0, I smaller than total horizontal rays. That's that constant up at the top of our file that determines how many rays that we want to shoot out to the right or to the left while we're moving horizontally. Okay, let's go ahead and calculate our ray vector. Our ray vector is going to be a new vector 2 of ray origin dot x and ray origin dot y plus I times vertical distance between rays. Okay, what's going on here? Well, I times, let's just work on the I times part. I times vertical distance between rays. Let's say there's 1 unit between each ray. So the first time this loops, I will be 0, which means it'll just be ray origin plus 0. Second iteration, I will be 1. So we said that there's 1 unit between rays. That means I will this expression will now be 1, meaning will be ray origin dot y plus 1, and just we'll keep on looping through that. Again, I'll show you guys a visual representation of this algorithm here in a moment in Photoshop. Next up, I'm going to do some debugging. I'm going to say debug dot draw ray. So I'm going to say debug draw ray, and the reason I'm doing this is I really want to have a visual representation of what we're doing and where our rays are pointing. And debug dot draw array will draw a ray in our scene view so we can actually look at how our rays are working. So we'll do ray vector, ray direction, times ray distance. Ray distance. And then we'll pass in a color of red. So what does this do? This draws a ray from our ray vector and then our ray direction scaled up by the distance. Remember, ray direction is a unit vector, meaning if we multiply it by a distance, we're going to get a vector in the direction of this vector, but of this length. Okay, so now that we've done that, now let's perform the actual raycast. The actual raycast is going to be performed by, so we'll say var raycast equals, or sorry, var raycast hit equals physics 2D dot raycast, passing in our ray origin, our ray direction, our ray distance, and then finally our platform mask. So now we can see an example of us actually using the platform mask. If you recall, the platform mask is what determines if an object is going to prevent our movement or not. Okay, you'll also notice I have a syntax error here. This should be raycast ray vector, not ray. Oh, come on, there we go. Some other important things to note about this line, we're using physics 2D and not physics. Physics 2D is what's going to operate on 2D rigid bodies and 2D colliders, as opposed to physics, which will operate on 3D colliders and 3D rigid bodies. Okay, then we're going to say if not raycast hit, then continue. Do not type in return. It might be, I've seen a lot of people who, when they do an early exit on a loop, they'll do like return. That'll just exit the entire method. We want to type in continue. So what does this code do? Well, this code says, if there was a raycast, then do something. Otherwise, continue the loop. You'll notice that the raycast hit class actually implements the Boolean operators, the Boolean equality operators. What do I mean by that? Well, if we decompile raycast hit 2D, we'll see that it has the implicit Boolean conversion. Because it has an implicit Boolean conversion, basically by saying if not raycast hit is by definition shorthand for if the hit's collider is not or is null. So that's just a little handy shorthand. Okay, so once we've done that, we now know that we hit something. So that's good. Then we want to do something a little weird, which I'll explain later. We'll say if I equals 0 and handle horizontal slope ref delta movement vector 2 angle between raycast hit normal and vector 2 up is going right, then break. Okay, first of all, we're going to run into a syntax error. Why? Because when I stubbed out handle horizontal slope, I forgot that it actually returned a value. Handle horizontal slope, this method right down here, it's empty, but it actually returns a value, and that value is a Boolean. Because our stub now returns a value, I'm going to simply return a value so that the code compiles. The value I'm going to return is false, and that'll prevent our horizontal movement from breaking. So what are we doing here? Well, we're checking to see if we're on the first iteration and the handle horizontal slope returns true. The handle horizontal slope will return true if we're on a horizontal slope. Then we pass in the delta movement and if we're going up right or if we're going left. But we also do something a little crazy here. We say vector 2 dot angle between the raycast hit normal and vector 2 dot up. That'll give us the angle between up and where we hit that object. So for example, actually, you know what, I don't want to jump back and forth between Photoshop. When we go and handle the horizontal slope, I'll show you guys the diagram of exactly what's happening there. Okay, so now we get to the fun part. Delta movement.x equals raycast hit dot point raycast hit dot point dot x minus ray dot x or ray vector dot x. We'll take a look at what this does here in a moment. I can briefly explain it. What this does is this does the actual constraining. If we hit something, then we can only move that far forward. Next up, we want to set the ray distance to mathf abs delta movement x. And I'll talk about why we have to do that again when we go into Photoshop. Then I'm going to say, if we are going right, delta movement x minus equals skin width. That means we have to subtract, if we're going right, we have to subtract off the skin width. Then we say state is colliding right equals true. And then and then we do else. So if we're going left, then we do the opposite. We say delta movement.x plus equals skin width. And then we say state is colliding left is true. Finally, we do one more weird thing, which I'll explain graphically. If ray distance is smaller than skin width plus 0.0001f, then break. That means something messed up. Okay, so this code looks a little bit scary, but let's go ahead and fire up Visual Studio or fire up Photoshop and take a look at why this works and the cases that it handles. I'm going to use some exaggerated ray distances just to show you guys. But let's go ahead and look at this. Isn't math fun?
Yeah, I love math so much. I don't have words.
Hold on. I'm going to do a really quick little palette here so I can quickly swap between colors. All right. Okay, so what we're looking at now is how we move the player. Let's look at the case of moving the player to the right instead of moving to the left. So here's the player, and the player is represented as just a box. And then let's say there's an obstacle this far away. So let's say there's an obstacle this far away, right? And he is moving to the right. Okay, let's step over everything that we're going to do. Let's say that we want to move this player from here all the way to here. Let's say that's what we're wanting to do. Now, obviously this isn't going to be valid, but let's show how the code that we just wrote will actually cause this to return to us in a valid state. And I'm also going to remove the sloping from this curve so that this example isn't ambiguous with when we actually do write code to handle slopes explicitly. Okay, so that's the player, that's an obstacle, that's our delta movement. Our delta movement is really big. Of course, our delta movement will rarely ever be that big, but in this case it's really big for demonstration purposes. Let's look at the code. First of all, are we going right? Is delta movement.x greater than 0? Yes, we are going right because this delta movement, let's call it 50 in the x and 0 in the y. Okay, ray distance. What is this going to do? Well, this is going to say math f.abs delta, delta movement dot, oh, come on, go away. Delta movement dot x plus skin width. So what is ray distance? Ray distance is this number right here plus our skin width. So let's say that little red bit refers to our skin width. So this is how far we're going to project out the ray. Let's to make this just a tad more clear, let's not consider the movement starting from inside of the player. Let's only consider the movement from outside of the player, which will make a little bit more sense. Okay, what's the ray direction? Well, if we are going right, the ray direction is to the right. If we're going left, it's going to be to the left. So our ray direction currently is a unit vector that points to the right. What is our ray origin? If we are going right, we start at the bottom right. If we are going left, we start at the bottom left, which means our ray origin is right here in this example. All right, now we loop from 0 to total horizontal rays. For every one of these, we construct a ray vector. The ray vector is going to be, let's say here, then it's going to be, let's say we have like a couple rays, so we have another ray here, another ray here, another ray here, and another ray here, right? And they're all separated by the maximum width. So in this case, we have 1, 2, 3, 4, 5 rays. So we loop 5 times. Then we perform the raycast. What's the raycast going to look like? Well, the raycast is going to look like this line right here. That's what the raycast is going to be. We perform that raycast for every one of these rays. Let's say that the only ray that we're worried about right now is this one right here. So we perform this green raycast. Okay, then we check to see, did it hit anything? Well, if we look at our diagram, it did hit something. It hit whatever this is, right? So because it hit whatever this is, that means this code will not break out of the loop and will continue on the loop. Then we do some horizontal slope funkiness, which we won't talk about in this video. Then we say delta movement dot x equals raycast hit point x minus ray vector dot x. What does that mean? Well, what's the point? What's the point? Seriously. What's the raycast point? The raycast point is right here. This is the raycast point. So what we want to do is we want to take this ray vector, this whole ray vector right here, and subtract it, or subtract the point, or take the point and subtract it by ray vector. So that's going to take this point and subtract it by the ray vector. So we're going to basically be going here. Now the funny thing about this value right here is this value happens to be the furthest to the right that the player can move without hitting an obstacle. Sound good?
Yeah, I got it.
So that is the furthest we can move without hitting an obstacle. So if that's the furthest that we can move without hitting an obstacle, let's just go ahead and set the delta movement.x to that value, which we do right here. We set delta movement.x to the furthest we can move to the right without hitting an obstacle. Then we say ray distance equals mathf.abs delta movement x. What does this do? Well, let's say we, I'm going to use another diagram for this. So let's say we have a character, right? And
Okay.
let's say we have steps. The first ray, I know we start at the bottom right in our code, but let's say at this example we start at the top right. So in this case, we will shoot out a ray from the top. We'll get this distance. The next time we shoot out a ray, we will only shoot that distance, right? But we hit a new obstacle right here. The next time we shoot out a ray, we will only shoot that ray out that distance. Then, the next time we shoot out a ray, we'll still only shoot out that distance. And then the final time we shoot out a ray, we'll only shoot at that distance. Notice that we have, this is kind of like a nice little optimization because we have less stuff that we're raycasting against, because we know that once we have hit something at this distance, hitting anything closer or further away than that distance is irrelevant because it's not going to change the furthest we can move forward without hitting an obstacle.
Alrighty, making sense so far.
Alrighty, the last thing that we want to do, or second to last thing that we want to do, is if we're going right, we subtract off the skin width. If we're going left, we add on the skin width. Why do we do that? Well, remember that the skin width is actually, this ray is actually kind of, you can think of it like it's shooting out right here. Which means when we get this number, this total movement that we can move forward, it's actually, there's an error in it. And that error is the skin width because we're shooting it from here. We need to fix that. We correct that by, if we're going right, we take off the skin width. So we subtract that from the total movement that we can handle. If we're going left, we add that skin width. So that's how we correct that error. Okay, the last thing that we do is if ray distance is smaller than the skin width plus a very small number, that means like we're colliding like, I don't know, we're colliding like right here. Then something went wrong and we just break out. That's just an error that might happen. Sound good?
It does indeed.
Okay, let's test this guy out. If I didn't make any mistakes, which I probably did, we should be able to move to the left and to the right. Okay, we can move to the right.
Drum roll, please.
Obviously, I don't have any obstacles, so let's go ahead and add some obstacles. I'm going to take the player, and I'm going to move him over here, and then I'm going to duplicate this dirt fall and move it up. And then I'm going to move my punji sticks over a little bit, duplicate this grass. I'm Actually, no, delete that grass. I'm going to duplicate this. I'm just going to make a little cage for him. And then hit play. And we are totally able to go inside of our stuff. Okay, so this is where we start debugging. So remember how we're showing those rays in the debugger or in the scene view? Let's go ahead and take a look at those rays while we're moving. So what I'm going to do is I'm going to keep the scene view open while... Are we even shooting any rays? You know, it might be possible that we're not shooting even any rays at all. Move horizontally if delta movement is greater. How do we debug this? Well, it's pretty simple. We just go here, we add a debug log ASDF. If we see ASDF in our console, we know we should be shooting rays. We do not. We're not shooting rays. Why wouldn't we be shooting rays? Well, there's a couple of reasons. Is total horizontal rays 0? It is not. That means the only way that we could not be shooting rays is if move horizontally is not being called. And you know why move horizontally is not being called? Because handles collisions defaults to 0 and we never set it to true. Okay.
I was just going to say reasons.
Yeah, well, that is reason right there. We made our handle collisions property, but we never set it to true, meaning that it's not handling collisions, meaning it's doing exactly what we told it to. So let's come up to our awake method, and let's go at the top and say our default for handle collisions is true. Let's come back into Unity and hit play. And we get some problems, and I think part of the issue is actually, there we go. That is better. Okay, the problem is we had the player kind of in the grass already, and if he's in the grass, his horizontal movement stuff just breaks down. That's because we're not handling vertical movement yet. But if we have him up here, we can see that he indeed does get constrained left and right based off of his movement. Let's try to move him up here. See, his foot right there gets hit by that collider. We also notice that he has a little bit of a deceleration to him and a little bit of an acceleration to him, and that's caused by our player controller. So let's go ahead and yeah, I think that pretty much wraps up what I wanted to do in this video, getting the horizontal movement put together.
I'm giving you an A.
It works. I'm surprised it works.
Wow.
But yeah, I mean, pretty much it looks like a big scary bit of code, but in reality, all it's doing is detecting the furthest to the right that it can move. And we can see that represented here graphically with just some really basic diagrams. So I think that wraps this video up, and we'll see you guys in the next one.